Hi everybody. In this lesson today we're going to talk about linear programming. At the top of the page you don't have to write down this quote, but this is a good example of why I really like linear programming. I think it is something that's really cool. It allows us to do something that without math would not be easy to do. And so from that quote you can see it was developed during the Second World War for solving military logistic problems. It is used extensively today in business to minimize costs and maximize profits. So the one reason I really like this is people are always asking me, when do I ever need this? When will I ever need math in my life? This is an example of when you need this. I mean, is everyone going to be into logistics? No, but you have problems. There will be problems in life that you're trying to maximize certain things or minimize certain things. And so this is an example of how to do that. When we talk about linear programming, there are some vocabulary words that are new to us, and so let's just take a few minutes to go through that. Linear programming, we just talked about it, a systemic way or a systematic way to set up a problem to maximize or minimize, that is, optimize a certain value. A lot of times it's called linear optimization, and so optimization is something, like I said, that is a big field in mathematics as well as business and other areas. Constraints. The constraints are the inequalities that define the constraints or limits of the situation. So for example, let's say you have a budget and you have to spend less than $1,000. That's a constraint. Let's say you need to have at least 10 people. That's a constraint. Anything that could be said as an inequality, and it's going to kind of define your situation. Feasible region. The feasible region is the shaded area. So we've been working on graphing and shading lines. We're going to continue with that. And this is kind of like, when am I ever going to have to use it? This is when you're going to need to graph and shade lines. It's the shaded area outlined by the constraints. And then the vertices of this area are your potential max or your potential min values. And so as it turns out, if you want to optimize something, the best way to do that is to use the vertices. So we'll kind of get into some of that so you can understand what I'm saying here. The objective function is the equation that represents what you are trying to maximize or minimize. So are you trying to maximize profits? Are you trying to minimize cost? What are you trying to get at? What is your objective here? That is the objective function. Okay, so I have an example here, and that is an example of a situation that might actually occur. So this person, Gillian, is planning a green roof that will cover up to 600 square feet. She will use two types of plants, blue lagoon sedum and raspberry red sedum. Each blue lagoon sedum will cover 1.2 square feet. Each raspberry red sedum will cover 2 square feet. Each plant costs $2.50, and she must spend less than $1,000. Okay, we need to be able to read through this problem and decide what are our variables, what are our constraints, what is our objective function, and we need to break it down. And so I thought before we would do that, I would show you what is a sedum plant. I actually have sedum in my garden. I didn't know that's what they were called, honestly, but they are, this is a pretty good picture of it. You might have seen these. They grow really well around here. So I have these in my garden. I don't know if mine are raspberry red or blue lagoon or what kind they are, but they grow well here. And so you might have seen them around. Maybe you have them in your garden at home. Okay, typically when we look at a word problem, we want to break it down and we want to find out even what are our variables. And as you read through this problem, there is a lot going on in this problem. So it's kind of hard to say what our variables are. Because as you look at it, you've got square feet, you've got two different kinds of plants, you've got a budget, you've got a cost, you've got all these different things. And so what are your variables? I personally think sometimes it's easier to start with the constraints. So the constraints are, again, what are the limitations? So here's Gillian. She has this problem. What are her limitations? Well, one thing that we know that we've said is she has to spend less than $1,000. So one of her constraints is going to be her budget. Another thing, which might not be as obvious, but as you read through here, I think you'll understand it, it has to cover up to 600 square feet. In other words, it has to be less than 600 square feet. So here's the deal. I think it's easier to start off with saying what are the constraints. And so the constraints are the budget and the area. Once we know that, then we can cut those out because constraints are not going to be the variables. So budget and area are not our variables. And so now maybe that has taken some other stuff out. What does that leave for our variables? Well, the other thing, and again, typically in this class, we're just dealing with two variables at this point. So what are two things that are here in this problem? And so we can say that X is the number of blue sedum plants and Y is the number of red sedum plants. I will encourage you in your variables when you're defining those to be specific. So don't just say blue sedum or red sedum. What about it? Is it the cost of each plant? Is it the area each plant takes? No, it's just the number of blue sedum plants and the number of red sedum plants. Those are our variables. Okay, so if those are our variables, those are our X and Y's, we should be able to come up with a budget. We're going to do a lot of this in standard form. That's AX plus BY equals C. Not always, but a lot of times. So let's think about the budget. We know that budget has to be $1,000. So as far as our AX plus BY equals C, it has to add up to $1,000. Well, what other dollars do we have? We have cost of $250 each. Now, it doesn't say which one's a red sedum and which one's a blue sedum. That means both of them, each of them, cost $250 a piece. So in our budget, we have a 250X plus 250Y. They're each 250 a piece. And if we add up together how many we have for the blue and the red together, it has to be less than or equal to 1,000. Now we have to think about the area. What is the area? We've talked about 600 square feet. Has to be less than that because it's up to. She has two types of plants. One of them takes 1.2 square feet. The other one takes 2 square feet. So our area is going to be 1.2x plus 2y is less than or equal to 600. Okay, that I think is a lot of times the hardest part is just setting up the variables. But now that we know the variables and we know the constraints, now we can start to put our graph together. And so we're going to put the blue sedum, number of blue sedum plants on the x-axis, the number of red sedum plants on the y-axis. So here we go with that. We need to decide what are we going to count by and how high are we going to count. And so this graph that I have here on your paper has 10 dark lines and then the midline in between each one and 10 dark lines going this way. These two are in standard form. We have talked about standard form and how to graph using standard form. So maybe before we set up our graph, we should, or before we put our numbers on here, we should figure out where we're going to have to graph this anyway. And so remember we talked about the cover-up method? So I'm going to use the cover-up method and find my table of values with the cover-up method, my x and y intercept. So if I cover up this x, then I take 1,000 divided by 250 and I come up with the y, and I believe that is 400. Going to cover up my y, 1,000 divided by 250, once again that is 400. Okay, let's talk about the area. Again, we're going to cover up the y, 600 divided by, we should have gone the other way. We should cover up the x, and 600 divided by 2 is 300. Cover up the y, 600 divided by 1.2 is 500. And so as I look at this, I can now see I need to count up to 500. So that's what I'm going to do. I'm going to count all the way up to 500. And so I'm going to go 100, you can go 50, 100, 150, 200, 250, 300, etc. And I'm just going 100, 200, 300, 400, 500. So take a second to set up your graph, and then we'll talk about actually graphing them. All right, one other constraint that is important that I forgot about is that x has to be greater than or equal to 0, and y has to be greater than or equal to 0, right? Because you can't have negative number of plants. So we need to include those two constraints also. So we actually have 1, 2, 3, 4 different constraints. And with those 4 different constraints, we're going to graph them and we're going to find out their intersection points, and this should make a this should make a quadrilateral of some kind. And you know what, as I read through here, it says Gillian must spend less than $1,000. Maybe we should change that to just a plain old less than. So I'm going to erase my equal to with that one just because it says less than. Okay, so we've already figured out our intercepts here, so let's go ahead and graph those. So this one's going to go from 400 to 400. It is a dotted line because I got rid of that equal to, so it is a dotted line. The x is greater than or equal to 0 and the y is greater than or equal to 0 is pretty easy to graph, so we can do that. And those you could probably argue they're already on the graph anyway, so they're there, but we are going to use them for shading as well. In fact, before we do our last equation, let's talk about shading. So we already said these are greater than, so we know it's going to be in this quadrant. Well, that's obvious, hopefully, because that's the quadrant we have. But how about this one? Should it be up here or down here? Well, it has to be less than, and with that little shortcut rule we learned the other day, y is less than means that it's going to be down here. So this is where it's going to be shaded. Don't shade too darkly because we still need to figure out the rest of the shading as well. But that's what we have for now. And then finally, our last line, that was over here. It has a y-intercept of 300 and an x-intercept of 500. So let's go ahead and graph that line as well. And with this line, we need to talk about what about the shading? Well, again, that's going to be an important part of what we're doing here, both the shading and the vertices. So let's figure out this shading. It is y is less than. So once again, it's underneath this solid line that I have. So this is my shaded area. Notice I did not go over here because it was supposed to be underneath the dotted line. So it's not over here. It just goes kind of up to this one corner right here. And it goes to this corner right here. And up here it was shaded originally, but the second shading didn't overlap it. And maybe I should have used a second color, but it didn't overlap it. So I'm actually going to erase that just to clarify that that is not part of it because it has to be both of them. It has to be both of the shaded areas overlapping each other that we're looking for. And so that was a vertex, that's a vertex, this is a vertex, and this is a vertex. And as it turns out, like I said in the beginning, when you do this, these are your constraints. This area is called the feasible region. So you've heard that word feasible before. It means what is possible. Well, it means, what this shaded area means is I could pick any number of blue sedum plants and red sedum plants that fit into this area, and it would fit into my budget, and it would fit onto the roof. And so any number of these would be less than $1,000 total, and would be less than 600 feet total. So this is the feasible region. This is what is feasible, what is possible. However, what I've been trying to tell you is that these points are the vertices. Those are going to be the best ones. So yes, anything inside here would work, but we don't want to know anything. We want to know what is the best one. What's going to give us the maximum or the minimum? Well, the maximum or minimum, yet what? We haven't talked about that yet. That's going to be our next step. But we need to find those vertices. And so I can tell that there is a point here, obviously. One vertex is at 400, 0. Another easy one, obviously, is here at 0, 0. And there's another one here at 0, 300. And the only one that's left is this one. Now, if I drew this accurately enough, I should be able to see it. But I might want to check it once I see it. So it looks to me like this is at 250 and 150. If you're not sure, then what you can do is you can take a guess and then plug it in and see. And so you can do that. If you take 250 here and plug it in and take 150 here and plug it in, it should equal 1,000. Now it's equal because it's on the line. It's not the shaded area, it's on the line, so it's equal. And it does equal 1,000. And if I plug it in here, 1.2 times 250 plus 2 times 150, that should equal 600. And when I plug it in my calculator, it does. It does equal 600. So this is my fourth point. Okay, those four vertices are the best possible solutions. Anything in here could work, but these are the four best ones. Best for what? Well, let's finish out the rest of the word problem. I broke up this word problem on purpose so that we could just focus in on pieces of it at a time. So the actual problem says that one of her priorities is to help control air pollution. To do this, she wants to maximize the amount of carbon dioxide the plants on the roof absorb. Blue Lagoon sedum absorbs 1.4 pounds of CO2 per year, and raspberry red sedum absorbs 2.1 pounds of CO2 per year. So how many of each type of plant should she plant to maximize the CO2 absorption? Let me give you one other hint here, and this is actually kind of goes with the previous part, but if you're not sure what the variables are, you look for this last sentence that says how many of whatever should she do. It's how many of each plant. So that is another way to know which one is your X and Y, is the type of plants. Okay, so her goal here is to maximize CO2 absorption with this equation, because she knows that this is how much each one absorbs per year, and so this is the equation we're going to use. What we do here is we take each vertex and we plug it into this equation to see which one will work the best to optimize it. Because once again, this area just shows us all the possibilities, the feasible region, but we want to know what are the best, and the best ones are always on the corner. Now, I will say that a lot of people can obviously see that 0, 0 is not going to do it, right? That's not going to maximize anything. However, I want you to get into the habit of plugging those numbers in every time, even though you can see it's not really going to work, it's not going to be the max. Let's go ahead and put it in anyway, because we want to get into that habit. Because sometimes it won't be as obvious and it'll trick you, and you'll think it is and it's maybe not. So I just want to make sure you get into the habit of plugging in all of them. Okay, so obviously 0, 0 does not give us the max. If we try another one, we can try 400, 0. And when I plug that in, I get 560. I'm going to try the next one. So when I plug that one in, I get 630. Next, I'm going to take the 250, 150 and see what that is. I will also remind you that it's important to keep your X and Y's in line. I know that seems obvious, but when you put them on the X and the Y axis, make sure whatever X and Y axis is also the X and the Y that you're using here, and don't get those two confused. And so when I plug into this last equation, I get 665. So we were trying to maximize CO2 absorption. And in case you've forgotten what we're trying to do, these are going to be pounds of CO2. And the one that maximizes it is this one down here, 665 pounds of CO2. And so that is going to be the one that Gillian picks, because that's the one that gets rid of the most CO2. And so she should plant 250 and 150 to maximize the CO2 absorption of 665 pounds per year. Now, 250, and that's again, we have to go back and remember which one is our X and which one is our Y. And so there's several different places in our problem that we can do that. One is that said that the red was the 2.1, that was the 150. So this one is the red sedum, and this one is the blue sedum. So all of that work to come up with the final answer that the best number of plants would be 250 blue and 150 red, so that she can maximize her CO2 absorption to 665 pounds per year. That is a lot of work, right? And so each problem here, you can tell, takes a lot of time, takes a lot of thought, but the advantage is in the end, you come up with your optimized solution. And so that's what's so great about this. We will continue to work on this in class next time.